Hello everyone, I'm Junkai and I'm going to introduce our work, Achilles, a framework of leaking secrets from signature schemes via Rowhammer tree. And the first thing about some background and the importance of signature schemes. Signature schemes serve as backbones for network security, such as network protocol, blockchain wallet, software updates, and secret machine transfer. However, most of the schemes are vulnerable regarding the fault injection attack, such as some widely used ECDSA, RNC, and some post-quantum attacks. All these attacks have some real impact CVEs. The framework injects faults into the parameter of the signature schemes because the parameters of schemes are loaded into memory cells in USENIX, and the Rowhammer bug allows the attacker to exploit the memory cells and tamper with memory data. However, we found some problems of existing works, such as many signature schemes are not analyzed. For example, BLS, BB-short, AGMA, and MLDSA. It is still unclear how we utilize the existing analysis for new signature schemes. So, in this work, we try to propose a common framework Achilles, which targets generalized signature schemes and can be used for discovering new vulnerable parameters, even in studied schemes, and helping identify new vulnerable schemes. So the background for a Rowhammer. Rowhammer attack is focused on tampering with the data in some DRAM, and in each chip of which DRAM there are multiple banks, and in each bank we try to flash the adjacent rows, and then in the middle of the row, the data on the middle rows will be tampered because of the physical property of the DRM. So, in the background of signature schemes, the idea is simple. The virus identifies the identity of the seller by using public parameters. And there are three functionalities such as keying, signing, and verify. So the first step of our framework is based on general definition of signature schemes. And it is actually a formal treatment of signature schemes. We include some key parameters in signature schemes such as randomness, message, hash value, and public key, secret key. All these key parameters will be considered to be faulted by the attacker. So the step 2 is about the game-based model against Shen. And we have displayed some oracles such as Shen, which is an oracle that sends a message and returns the signature output. And FIX, a formalization of the Rowhammer fault. OF is an oracle which uses FIX and tries to inject the fault in some key parameters. Here we go into the important part of our framework, experiment. The game experiment indicated two kinds of capability of the attacker. You can see in line 5, the attacker can output a valid signature on a new message, which indicated that the attacker already knows the secret key. And in this case, the fault must occur on the public parameter, because if the fault occurs on the secret parameter, the whole resulting signature can be considered a new signature regarding to a valid secret key. And in this case, the attacker cannot leak any information. So if the attacker wants to use Rowhammer and get some meaningful faulty signature, the fault occurs on the public parameter in this case. And in line 6, the attacker tried to output some valid faulty information and a valid signature on an existing message, which would query in OF step. In this case, the fault must occur on the secret parameter, because if the fault occurs on the public parameter, the fault information is meaningless to the attacker. So, target public parameter and secret parameter, we have designed the whole algorithm to recover the secrets. The first is about the fault occurs on the public parameter, and we have designed an algorithm called differential fault analysis. And in our algorithm, we try to parse each schemes into some symbol representation, and we then do enumerate all possible parameters and try to inject fault in it, and get the faulty signature by the representation of symbols, and try to see if it can be exploitable by the differential analysis. And for the secret parameter, I have designed the algorithm as C, also known as the secret correction attack. We try to enumerate all possible secret parameters and get the representation of the faulty signature. We try to correct the faulty signature to a valid one. If we succeed, we can use the correction term known as delta as bit latent. So an example is that to use the algorithm, the attacker need first instantiate with a specific scheme. We use DDSC as an example. In the teaching process, we compare all the parameters and we input the equation of relation of these symbols. And we also implement the sending process for some equations of symbols. We then use DFA and HCA to try to get some faulty representation of the faulty signature. And we can see if the signature equals the two-term, and we can call in HCA, we can correct them to the valid one, and in DFA we can compare it with a valid one to have a simple subtraction will yield a secret key. We have found that the process can be automated by using symbolic calculations. We have designed a program called the AutoWarner to use from this automation. The input of the AutoWarner is description of the symbols and the description of the equations of the symbols. And the output is some potentially vulnerable parameters. The result from the AutoWarner is in the right in table 3. We follow the idea of extending offline memory profiling, on-level injection, and post-harm analysis for performing an attack on SCORM evaluation. You can see that attacker without root access co-located on the remote server with the victim do some memory profiling, on-level the injection, and post-harm analysis. In the memory profiling, we first run drum dig to get the band function of our drum, from which we can know if two addresses are in the same byte. Then we profile 12 GB of the physical memory. And the result is and below. And in the online fault injection, we utilize the behavior of the linear body allocator, which allows us to do memory message by reading the vulnerable page and convince the victim to use the pages to store the parameters. The challenge is that the fault must occur in a limited time window between a parameter's initialization and its subsequent use in computations. Our solution is that we use OS signals. The attacker processes some register the signal to track the right kernel into switching the victim process of the code to solve the problem of the limited time window. And the post-harm analysis, we are able to recover the secrets using our equations, using our algorithm described above. In DFA, we are need to run faulty signature for full recovery, such as BDSA and MLDSA. And in SC, we need hundreds of faulty signatures we also need to find the remaining bits. And we have designed a new algorithm to find the remaining bits known as scorer. And we have compared the scorer with Jones' algorithm and data. Our algorithm more efficient. And one. Then is some countermeasure. Some specific difference of signature schemes, including liquid read and cryptographic schemes, verifying after signing and redundancy check. And WorkFileCL has adopted our suggestion and implement verifying after signing and redundancy check for RSA and DSA. And is in this CVs below. In our work, we have also shown that these countermeasures can be bypassed by faulting the opcode. Can see the paper for the ticket. We also introduced some feed-fault fault injection and compared them in our work to Rowhammer. So we asked the question, can physical fault injection achieve similar results? But the physical fault injection such as optical radiation, water clock lynch, electromagnetic pulses, and temperature attack. So we found that the temporal and spatial processing of these attacks do not meet our requirements. These attacks do not allow remote attackers to, which are not some appropriate in this case. So for more insights, code, and data you can find in our website. Thank you for listening.